video, we discuss how to solve recurrence relations using telescoping sequences. In particular, we went through an example to show a way to solve recurrence relations of the form an equals an minus 1 plus fn, where the sum from k equals 1 to n fk has a known closed formula. If you rewrite the recurrence relation as an minus 1 equals fn, and then add up all the different equations with n ranging between 1 and n, the left-hand side will always give you an minus a naught, the last term minus the initial term. The right-hand side will be the sum from k equals 1 to n fk, which is why we need to know the closed formula for that sum. However, telescoping will not help us with a recursion such as if we had an equals 3an minus 1 plus 2an minus 2, or actually just plus 2. Since the left-hand side will not telescope, you will have minus 3an minus 1s, but only one an. However, we can still be clever if we use iteration. We have already seen an example of iteration when we found the closed formula for arithmetic and geometric sequences. The idea is we iterate the process of finding the next term, starting with the known initial condition up until we have an. Then we simplify. In the arithmetic sequence example, we simplified by multiplying d by the number of times we add it to a when we get to an, to get from an equals a plus d plus d plus d, and so on, plus d, forgot that last part, to an equals a plus dn. To see how this works, let's go through the same example we used for telescoping, but this time use iteration. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. All right, let's do an example here. I'm going to erase this and I'm going to copy paste my example right here. So use iteration to solve the recurrence relation an equals an minus 1 plus n with a naught equals 4. Again, start by writing down the recurrence relation when n equals 1. This time, don't subtract the an minus 1 terms to the other side. So we have a1 equals a naught plus 1. Now a2 equals a1 plus 2, but we know what a1 is. By substitution, we get a2 equals a1, which is a naught plus 1 plus 2. Which is a1 plus 2. Now go to a3. a3 equals a2 plus 3, which is, that whole thing right there is a2, so that's a naught plus 1 plus 2 plus 3. Using our known value of a2, we know that since a naught equals 4, we know that a3 equals a naught plus 1 plus 2 plus 3. We notice a pattern. Each time we take the previous term and add the current index. So an in general is just going to be, I think I'm going to need 4 of these here technically. A naught plus 1 plus 2 plus 3 plus dot 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 plus n minus 1 plus n at the very end. Got that. All right. Regrouping terms, we notice that an is just a naught plus the sum of the integers from 1 to n. So since a naught equals 4 right there that I mentioned earlier, that means, and I'm going to make a little bit more room for myself here. That means that an equals 4 plus n times n plus 1 all over 2. Iteration can be messy, but when the recurrence relation only refers to one previous term and maybe some function of n, it can work well. However, trying to iterate a recurrence relation such as, if we had an equals 2an minus 1 plus 3an minus 2, will be way too complicated. we would need to keep track of 2 sets of previous terms, each of which were expressed by 2 previous terms, and so on. The length of the formula would grow exponentially. It would double each time, in fact. Luckily, there happens to be a method for solving recurrence relations which works very well on relations like this, and we'll talk about that in the next couple of videos. So again, I want to emphasize we've gone through rather complex ways of solving recurrence relations, but I'm about to show you all a really interesting and unique and rather simple way of solving recurrence relations using what are called characteristic roots and characteristic polynomials and characteristic equations. So I'll see you all in the next couple of videos.